Good afternoon. Today we are going to go over different set concepts and set operations. So in last class we saw that whenever there is a set A, which we are going to say is a subset of set B, then we saw that every element of A is also in B. So formally, if we want to write, we can say that for all x, whenever x is a member of A, then that implies that X is also member of B. So that's how we are formally writing the definition of subset. Now here, from one side, it is always given that everything in A is part of B, but it is not given the other way around. So when we also have, for example, everything in A is in B, and vice versa. And if we have that everything in B is also part of A, then this is the condition of set equality. In this case, A will be equal to B. In this case, there is possibility that A and B are same sets. It is possible that everything in A is in B, and then B does not have anything other than the elements of A. So there is a possibility, but it need not be always the case. So sometimes it might happen that everything in A is in B. So this is acceptable. Everything in A is also in B, where A and B are same sets. So both these possibilities come under subset definition. And when we have that the formal definition from both ways, then that is a condition where both sets are same. So everything in B is also part of A, everything in A is also part of B. Now there is a next definition we are going to say, which is proper subset. Now, in case of proper subset, where the equality is not possible, so we want this part of the definition that for all x, everything, whenever x is member of A, that implies x is member of B. But we want to get rid of the equality. So in that case, there must be at least one element which is in B, but which is not in A. So that's what this part says, that for all, so these are the universal quantifier. It is true for all x. So this upside down A is called as for all or universal quantifier. And mirror image of E, this is for there exists. There exists, or it is also called as existential quantifier. So in this case, at least one x should be there such that x is in B, but x is not in A. So that enforces that B has at least one value which A does not have. So this equality will never be possible. So in this case, in proper subset, A will always be a proper subset of B, and that we define by A subset B. So it is not possible, the equality symbol is now gone from the subset, and A will always have less number of elements than B. So in other words, we can also conclude that since everything in A is in B and B has something more, so what relation will be there between cardinality of A and cardinality of B? So cardinality of A is number of elements in set A. Cardinality of B is number of elements in set B. So what will be the relation between these two? Will they be equal? Yes. So cardinality of A will always be less than cardinality of B. When we talk about A, is a subset of B. In this case, we have cardinality of A less than equal to cardinality of B. When both have equal sets, A is equal to B, in that case, we are going to say cardinality of A is equal to cardinality of B. Okay. Now we will see, we haven't yet seen the definition of cardinality, but cardinality is number of elements of that set. So this is the next slide where it says, so I can remove this or you can remove this if you don't want. So these are the black marks. So we can remove this. So I just wrote it as one example. So maybe we'll have a new slide. So by definition, cardinality is number of distinct elements in the set. So if you have any element which is repeated twice and thrice, we are going to count it only once. So that is the distinct elements in the set. So here are some examples we'll see. If we are talking about null set, then null set means that set is empty. In other words, we also show null set like this. So if we have to find cardinality of this set, there is nothing here, so cardinality is 0. If we are talking about set of all alphabets S, A to Z, then cardinality of that set will be 26 because there are 26 alphabets. If we are talking about this set 1 to 3, there are 3 distinct elements, cardinality is 3. And cardinality is shown by this symbol around the set. Now, if we are talking about cardinality of set of integers, then that will be infinite. Another thing is when we are talking about a set containing null elements, for this, the cardinality will be 1 since we have one element. That element is null. So this is the difference we talked about the set containing null and null set. So set containing null is not a null set because it still has one value in it. So the cardinality of that set is 1, but the cardinality of null set is 0. Now, another thing, since we are talking about distinct elements, if I have set A 1, 2, 3, 4, we can say the cardinality of set A, since we have 4 distinct elements, is 4. If we have set B in which we have some elements which are repeated, then for this set also the cardinality is 4. Although if we count individual, there are 1, 2, 3, 4, 5, 6, 7 members, it appears to be, but 2 is appearing twice, 3 is appearing twice. Distinct elements are 4, so cardinality of B is also 4. So we'll disregard if the same element appears twice or thrice. This is exactly same as saying we have 1, 2, 3, 4, or it is the same set as set A. Now, forward set, maybe I will delete these too many markings. The forward set is all possible subsets of a set. So if you say my set, so let's say my set A is A is 1, 2, then what are the different sets which will be subsets of A? So we know that if we have a set, let's say A1, which only has 1, then that will be a subset of A. If we have another set A2, which only has 2, that will also be subset of A. If I have another set A3 having 1 and 2, that will also be subset of A because we know that A can be subset of itself because of the equality. So there is a possibility that A is equal to A. So the same set is also subset of itself. then if you pick the less number of elements from that set, so if I make a set A1 having just 1, A2 having just 2, then all these will be possible subsets of A. So I can say A1 is a subset of A, A2 is a subset of A, A3 is a subset of A. Another possible subset is when we saw null sets, we saw that since null is nothing, so if you pick any set, let it have any elements, null set will always be subset of any set, right? So if we consider that our A4 is equal to null set, then we can say that A4 is also subset of A, or in other words, the null set is subset of 1, 2. Okay? If we have nothing and if we are having something, then that is going to be subset of anything a set has. So null set is also subset of itself, because we can say that subset does allow equality. So this, for 2 elements, we can have 4 possible subsets. Now, if I think by conditional statements also they have proved somewhere, maybe not here, but I think they have proved somewhere that how the subset definition is. So I think it's here. So whenever we say A is subset of B, we want that whatever member A has, B also has that member. So it is a conditional statement, right? Conditional statement, P implies Q. So if you see the truth table of P implies Q from propositional calculus, so if both are true, then this implication is true. If both true implies false, then this implication is false. If false implies true, then this implication is true. If false implies false, this implication is true, right? So the implication is only false if true implies false, right? Now, in this case, if we consider that for null set, whenever X is member of A, X is also member of B. Now this membership itself is going to be false because there is no element which is member of null set. So P is false always in case of if we are trying to look for this conditional statement, and we are going to say if something is member of null set, then it should be member of some set A, then null will be subset of that set, let's say. Then null is member of any set, that is going to be, this conditional statement is always going to be false. And since false implies, so we don't, it doesn't matter whether the Q is true or Q is false, our result of implication is always true. So if I say a null is member of some set, then null is member of some other set. So that implication will always be true, and hence null is a subset of every set. So kind of looking at the same thing from proof side of it. It need not be it's okay if you don't understand this proof right now, but just you will understand that since any member will never be part of null set. Sorry. So if we say that particular X is member of null set, and if it implies that X is member of A, then null is a subset of A. But this side is always going to be false. Hence, false implies whatever is always true. And hence, this statement is true that null is a subset of all sets. Logically, if you look at it, if I have nothing in any set, that will always be subset of set having something. So that's another way to look at it. So if we have to find power set for any given set, we are going to take different combinations of the members of the set, and we are going to find subsets of that set. So let's say we have, now let's assume that we have set A having just one element. Then what will be power set of A? All the subsets of this set, which is null set, because null is subset of all sets. And another set will be the set itself. So I'm trying to find out the correlation between cardinality of A and cardinality of power set. So power set is combination of all subsets. Okay, so all subsets of A. Now power set has two elements. If A has two elements, we saw that the power set has null. We can write it in this way, or empty set. Then 1, 2, and 1, 2. So if A has two elements, power set has 4 elements. How about if A has 3 elements? 8, yes. So power set has 8 elements. So empty set, then set 1, 2, 3. We can also combine 1, 2. That will also be subset of 1, 2, 3. We can have 2, 3, or 1, 3, or 1, 2, and 3. 2, 3, 4, 5, 6, 7, 8. So there are 8 possible sets which are subsets of A. So here, if A is 3, 9, power set has 8 elements. So what is the correlation? If I say cardinality of A is equal to n, what will be cardinality of power set of A? 2 raised to n. So those will be combinations, different combinations. So if I have 4 elements in power set, I will have 16 possible elements which I can find, or 16 possible subsets of that set. Now we are going to look at the So here is another definition. So specifically we used in relations and functions that whenever we have elements in the particular set. Now this is not actually a set. Here this is called as n tuple. So it has n elements in such a way that you would have distinct sets A1, A2 up to AN. And if you take product or Cartesian product of these sets, then the way it is arranged is that the first element will come from set A1, second element will come from A2, and the last element, nth element, will come from set AN. So such ordered, you can say that ordered collection is called as n tuple, and we'll see when that happens. So for example, if we say that the ordered pairs are AB and CD, then they both can be equal only if the first element is equal to first element and second element is equal to second element. Now, unlike sets, here the order matters because we want the first element to come from the first set only, so we cannot change the order. Like in set, the elements we can change the order because the meaning is that we are only concerned about the membership. So as long as I know one is member of A, two is member of A, whether I write it as 1, 2 or 2, 1, it's the same thing. But whenever we are talking about ordered in tuple, we want that the order is maintained. So the first element always comes from A1, second element always comes from A2. So in this case, A1 and A2 is not equal to A2, A1. So they both are different things. So that's how the ordered pairs work. So let's take one example. So this is example Cartesian product. So we will take one Cartesian product and we will see. So I will take it on another slide. Already too many markings. Insert. So let's just see the definition of Cartesian product and then we will take one example. Function we don't want yet. So if you look at the Cartesian product, it is between the sets A and B, then every time we are going to have all such combinations where the first element comes from A and second element comes from B, and all such possible combinations we are going to add, and that we are going to call it as a Cartesian product. Now, here is one example. A is equal to AB and B is equal to 1, 2, 3. So let's take the same example. A is equal to AB and B is equal to 1, 2, 3. So when we take Cartesian product, it is all possible combinations of the elements where the first element is coming from A and second element is coming from B. So if I take A as a first element, A can have second element 1, can have second element 2, can have second element 3. So all possible pairs, since there are two sets, are A1, A2, A3. Now, those are all possible ways in which we can combine the elements in such a way that first element is A. Now, how about if first element is B? Again, B can combine with 1, 2, and 3. So that will give me B1, B2, B3. Any other possible combination is there where first element comes from A and second element comes from B? Do you think any other element or pair we can add? So those are the only possible pairs we can have with these given sets. So if you count the number of such pairs we are getting here, the number of such pairs are 6. Okay. Now here let's see the correlation. So the cardinality of A has 2 elements. Cardinality of B has 3 elements. And if we find out the cardinality of A Cartesian product B, then that is 6. So is there any correlation between these numbers? Yes, that's right. That's a product of cardinalities of A and B. Okay. So whenever we have a given set, we can expect to see these many elements. So if I know my A has 4 elements and B has 3 elements, then we know that in Cartesian product, I'm expecting 12 elements and so on. So in this case, now you can see that here A1 is not equal to 1A. Because if I say 1A, it means my first element is coming from set B and second element is coming from set A, and that will never be part of A Cartesian product B. That will be part of B Cartesian product A. Right? So if I take B Cartesian product A, my first element will come from B. So with 1, I can have 1A, 1B. Similarly with 2, I can have 2A, 2B. Then I can also have 3A and 3B. So similar to a Cartesian product B, here also the number of expected elements will be 6, because that will again be, if we write an equation, B Cartesian product A cardinality will be cardinality of B multiplied by cardinality of A. And since multiplication is commutative, we will see that both the numbers, the number of elements are going to be same. So both are going to give us 6 elements, but then elements will be different. So here the elements are 1A, 1B, 2A, 2B, 3A, 3B. So those 6 elements we get if we do Cartesian product of B Cartesian product A. Okay. Now sometimes you will see that in book, what they have done is they have asked what is A square. So what will be A square? A square is another way of saying A Cartesian product A. So if my A is, let's say, AB, and I'm going to take A one more time, and then I'm going to find the elements. Now in this case, since both elements are same, it doesn't matter which way we are doing. So it is still both the sets are same. So in this case, we are going to get same elements, and we are going to say A square is equal to AA, AB, and BA. Okay. So since A has 2 elements, the Cartesian product will give us 4 elements. Similarly, you will see that we can do A cube, where it is A Cartesian product A, Cartesian product A. Now in this case, again, you can break it down. Since all the elements are A, you can either have it as a square Cartesian product A, where these are my elements, and then I'm going to combine those with A. So that is also fine. So B, sorry, B. So that might be A, then B, then ABA, ABB, and so on. You can do the other way around. Since all are A's, you can also do it like A Cartesian product A square. So that will also give you similar result. So you can do it in both ways. So this is also correct and this is also correct. Although the you can say that the sequence might change, it should give you same number of elements and so on. So since it is the same sets, it is we can do it both ways. If we are talking about A Cartesian product, B Cartesian product, C, then we cannot say that these are same. These are not. But since these sets are all A's, we can have it in both ways. So how will we do A Cartesian product A square? So my first element is coming from set A, and my second element is coming from set A square. So that will give me A, again A, B, A, B, A, B, B, and so on. So the elements will match, although the sequence will not match. And here there is another example where we have 3 sets A, B, C, and every set has its own element. So I will just copy and paste it on the next slide, and then we can do this. So here we have A, B, and C given to us, and we want to do Cartesian product of it. So since the first, so here every element will have 3 elements inside. right? Because one element will come from set A, one from B, and one from C. So if we start from the elements from A, we can say 0. We are going to combine with, let's say, first element of B and first element of C. Then we take 0 again, first element of B and second element of C. Then again first element of A, first element of B, and third element of C. Now next, if we take first element of A, second element of B, and first element of C. So we are going to do all possible combinations. So then first element of A, first element of, so second element of B, second element of C. 0, 2. Then we can now have second element of A, which is 1, and all the same combination again. Zero, you will have 1, 1, 1, 0, 1, 2. 2. So those are all possible elements from the Cartesian product of ABC. And we saw that here there are 2 multiplied by 2 multiplied by 3. So it should be 12 possible values. Okay, so basically all possible combinations. So mostly in this book we will see that we are talking mainly about pairs. So A Cartesian product B. Now another possibility of showing values in the set are the set, like set builder notation. When we discuss this briefly, that P is some predicate and all set elements will be such that they satisfy some predicate. And we saw one example where P was a prime number. So if I say X is belong to some set D for whenever Px is true, then when I say Px is a predicate of being prime, then we will know that the set will be set D will be all prime number set. So maybe 2, 3, 5, 7, 11. So here the predicate is given that the absolute.
Go back one slide.
Yeah.
Okay, no.
So here we will have 12 values, and that will happen when you take all possible combinations of A's, B's, and C. So depend how the order you choose, how you take. But generally how I take is I take first element of all sets, then first element of set A with second element of first element of B, and then all combinations. So 0, 1, and all possible combinations. 0, 1, 0, 0, 1, 1, 0, 1, 2. Then second, 0 with second element and all possible combinations of C. 0, 2, 0, 0, 2, 1, 0, 2, 2, and so on. So it depends. You can take it in different ways. The order will differ, but you will get the same elements. So now here the given predicate is that the predicate X is absolute value of X is 1. So what are the possible values when we say absolute value is 1? It means either it can hold +1 or +1 or -1. So those are the only 2 values where the absolute value of 1 will be as X. Okay. So So we from that predicate we find the elements of the set which are -1 and 1. So every time it won't be possible that we have the elements given to us. Sometimes it is in form of set builder notation. Sometimes it is in form of some predicate, and then whichever values satisfy that predicate, those values will be part of my set. So now we are going to move to easier part, which is the set operations. Now you might have seen set operations already. So basically there are 4 basic operations. This is called as union operation. This is called as intersection. Then negation, this is called as set difference. Set difference. And then we have this operation, which is also called as symmetric difference. So we are going to take one sample set, and then we are going to see. So they have also added complementation, which is what if I have set A, what will be the complement of that set. And that is also another operation. Now here is some discussion that we after this we are going to talk about some set identities also. And we are after set theory, we are going to see propositional calculus. So that will be if you have some values, how you are going to, or if you have some statements, how you are going to convert into propositional calculus. And then similar things, we are also going to see the truth tables in Boolean algebra. So the operations, we will see that it will be similar to what operations we saw in the propositional calculus. If those are similar to what we will see in Boolean algebra. Typically, you will see that the propositional calculus and Boolean algebra, the operations are very similar. With context of set, some rules are similar, like De Morgan's laws and set identities. Those might be same. Now, if we have sets A and B, then the union of set A union B is denoted by A union B. And by definition, it is such X which is either member of A or member of B. So when we say it is either member of B or A or B, what happens when it is member of both? It is included in the union. So that member which is common to both is also included in the union, but it is included only once if there are some common elements. So here they have shown one example 1, 2, 3, and 3, 4, 5. So using Venn diagram, when I say show set A, now A has 1, 2, 3, and set B has 3, 4, 5. So 3 is the common element between A and B. So 3 comes in both the sets. So 3 is part of both the sets. So we can say that 3 is in the intersecting area. And in this case, which A union B are all the elements which are part of either A or B. So my union set will be 1, 2, 3, 4. Okay. Now, what will be intersection? It is defined as A. This is intersection sign B. And it is all the elements X which are part of A and which are part of B. So for the same set, we showed just now 1, 2, 3 was the common element which was part of A as well as B. So A intersection B is 3. That is the only element which is common to both the sets, and this area is also called as intersecting area. So those elements which fall on the intersecting area are called or said to be inside intersection. Now, another definition is complement. So again, depending upon our universal set, the elements of set A are there, and then whichever elements are not part of A, those are called as the complement. So for all x, where x is part of the universal set, but it is not part of A, such elements are called as complement. Now in different books, the complement is shown differently. So in some books, it is shown as A dash. In some books, it is shown as negation of A. In some books, it is shown as A, C, small c, A raised to C, which is also complement. A dash or A, C, or A, all are used to show a complement, or our usual A and bar on top of A. So for example, here I have given, if you consider A is 1, 2, 3 and some universal set 1, 2, 3, 4, 5, then in that case, our A complement will be 3, 4, and 5, which are not part of A, but which are part of universal set. So another example they have given is if you have for example, so if universal set is positive integers less than 100, so our universal set will have all the elements. So positive integers, so it should start from 1 and less than 100, so it will go all the way up to 99. Now, what is the complement of x where x is greater than 70? So x is again, x is part of the universal set. So we have now range of x that x is greater than 70, and we also know that x is less than 100 because it is coming from the universal set. So the possible values that x can hold, x can be 71, x can be 70, so up to 99, right? So what will be, so this is my set A given to me. Now, if I am asked to find out A complement, so this is set A, which has all x's in such that x is between these two range. So what will be my A complement? All the elements which are in A will not be part of A complement. So in other words, we can also say that A complement is universal set minus A. So if you remove all the elements which are there in A from universal set, then you get A complement. So those will be the elements 1, 2, 3, 4 up to 70. Because after 71 to 99, that will be part of my set A. So in other words, I can say A complement is x such that x is a positive integer and x is less than equal to 70. So since it is very subjective, if your universal set changes, your A complement will also change. So depending upon what is your universal set, the elements in set A complement will change because it is universal set minus or universal set. From that set, we are going to remove all the elements of A. Now, what is set difference? We just discussed briefly that if A and B are two sets, then whenever we do A minus B, we remove all the common elements from A. So whichever are the common elements between A and B, we remove that. Now A might have some elements which B doesn't have, so those elements will just remain as it is. So the other definition of a set difference B is A intersection B complement. So whatever is in B and A, those we are going to remove. In other words, that element should be in A and that element should not be in B. So for example, if we take another example, or let's say we take the same example of A and B. So we had A as 1, 2, 3. 1, 2, 3, and we had B as 3, 4, 5. So when we take set difference 1, 2, 3, 4, 5, what we do is from A, we remove everything that B has. Now, A does not have 4 and 5, so it doesn't matter to me. So whatever A has, I don't want that element. So sorry, whatever element B has, we want to remove it from A. So this part B, we want to remove. And since A only has 1, 2, 3, and 3 is part of B, only 3 gets removed from A. So if I have to have set difference, it will be 1, 2. So you remove from A, you remove everything which is common to A and B. Right, so this is another way of saying A minus B. So A minus B is same as removing everything which is common to A and B from A. So here from A, we are removing only 3, which was also part of B. We don't care what else B has. Okay. As long as it is part of A, we have to remove it. So this is called as set difference. Now, how about B minus A? Anyone, what will be B minus A? So again, 3 is common. So now 3 we have to remove from B. So it will be 4, 5. Now another very symmetric. So the next operation is symmetric difference, and symmetric difference operation is also called as, so I think there is something overwritten here. This was the definition. So symmetric difference is shown as this symbol, and it is also called as, typically when we go to Boolean algebra, propositional calculus, it is also called as XOR or exclusive or. So all are same things. Exclusive or. Now when we say A union B, we always say either in A or in B. Or in both, right? So we are not really removing the elements which are in both. Only while calculating cardinality, we are considering that, or we are counting that element only once because it was present in both. But it will still be present at the union set. So this union is treated as, or also called as inclusive or. So it is either or, but when it appears in both, we are including that element as well. And symmetric difference is also looked at it as a exclusive or, meaning it should be either in A or in B, but not in both. So either in A or in B, but not in both. So in other words, whatever elements are there in the intersection, we don't take those. So that element must be either in A or in B, but not in both. So we are excluding the intersection part, and that is the definition of symmetric difference. So here they have given one example. Let's say our universal set is a set containing 10 elements from, so here I don't have space. So let's take this example. So here our universal set has 0 to 10 elements, and then set A and B. A has 1, 2, 3, 4, 5. So 1, 2, 3. And B has 4, 5, 6, 7, 8. So 4 and 5 are common elements. And then I have 6, 7, 8. What will be element outside of the circles and inside the rectangle, which are not in one of these sets, which is 0, 9, and 10. Right? Now, if I have to find the symmetric difference, then those are elements either in A or in B, but not in both. So those are, we are only considering elements which are either in A or in B. We are not considering the elements which are in the intersection. So this we are not going to take. So we are going to take 1, 2, 3 and 6, 7, 8 from B, because those elements will not occur on the intersecting area. So by definition, we can also say that the asymmetric difference B is whatever we had for A union B. From that, if we remove the elements from A intersection B, it will give me the symmetric difference or exclusive OR. So the intersecting part, the elements which are present in both, we are excluding those elements, only taking the ones which are exclusively in A or exclusively in B.